Now that we know what rational numbers and irrational numbers are, let's try to think how we can identify whether a given number is a rational number or an irrational number. For this purpose, the decimal expansion of the given number will give us a clue. Let's analyze this. In the case of a rational number, the decimal expansion will either be a terminating decimal expansion or a non-terminating recurring decimal expansion. Now, what do I mean with this? Let's try to understand this. Well, let's start with this one, a terminating decimal expansion. Say you have the rational number 3 by 4. If you divide 3 by 4, you will get 0.75. So this is the decimal expansion of 3 by 4, and you can see that this is terminating because it stops at this place. So it's exactly 0.75 and it stops, right? So it's a terminating decimal expansion. Now, if you take the fraction 1 by 3, you will see that it's 0.333 and it keeps going on like this. It never ends. And we can write this type of a decimal expansion as 0.3 with a bar above the repeating part. So for example, let's take another example. 1 by 7 is 0.1428571428 and it goes on like that. So I can write this as 0.142857 with a bar on top because this is the repeating part. It keeps repeating again and again in the decimal expansion. So you can see that these type of decimal expansions are non-terminating because they do not end, and they are recurring because they have a clear recurring part. Let's take one more example. Say you have 0.1232323. You can see that only 23 is getting repeated, right? 1 is not getting repeated. So this can be written as 0.123 with a bar on top of 23. Alright, so we have seen that any rational number, when you convert it to its decimal expansion, you will either get a terminating decimal expansion or a non-terminating recurring decimal expansion. Now, let's analyze what happens in the case of an irrational number. In the case of an irrational number, the decimal expansion will be non-terminating and non-recurring. It will be non-terminating, that means it will never end, and it will not have any recurring part. Let's take an example. 0.010011000111 etc. We can see that there is no set of digits in the decimal places that gets repeated again and again. So this is an example of an irrational number. Let's take a few more examples. Say you take root 2. The decimal expansion of root 2 is this one over here. You can see that there is no repeating set of digits and it does not end. Similarly, the decimal expansion of pi is this one. It's 3.14159 etc. You can see there is no set of digits that gets repeated again and again in the decimal places, and it does not terminate. So you can see that for an irrational number, the decimal expansion will be non-terminating and non-recurring. There's an interesting side note over here. In many geometry problems, we approximate pi to 22 by 7, but pi is not 22 by 7 because it's an irrational number. It cannot be expressed in the form p by q, but taking pi as 22 by 7 is only an approximation. Now, let's quickly revise what we have learned. The property that we have learned is for a rational number, the decimal expansion will either be terminating or non-terminating and recurring. For an irrational number, the decimal expansion will always be non-terminating and non-recurring. Now, with these properties, when you are given a decimal expansion, you can clearly know whether it's a rational number or an irrational number. For example, if you are given this decimal expansion, you can see that it's non-terminating and non-recurring. Therefore, it has to be an irrational number.